So hello, I'm going to give an overview about my work for my PhD at the University of Liverpool. And so our goal was to build a machine learning model to be able to do in silico co-crystal screening. So I will start by describing the whole project roadmap as it started and how it ended up. So first of all, we wanted to define what is a co-crystal and to extract as much information as we could from the co-crystals in the candidate structure database. After that, we wanted to define the problem and then select the best machine learning algorithms that we can use to perform in silico co-crystal screening. And after that, we applied this methodology for a very limited case of co-crystals, which is the pi-pi co-crystals. So after the successful application for this case study, we wanted to scale this up and cover the whole co-crystals in the CSD. To do that, we studied different ways of how to represent our data, how we can tune the machine learning model, and also to add some uncertainty estimation to the predictions, and then how we can gather data from literature and then benchmark and compare our models to other models that have been built for the same purpose. So after that, we also wanted to deploy the whole model and then provide an online graphical user interface such that any user can be used and for in silico co-crystal screening quite quickly. So to begin with, what is a co-crystal? So a co-crystal can be formed when we combine one molecule with a second molecule, and which are connected with several types of interactions, such as hydrogen bonding, halogen bonding, or pi-pi stacking. So when these two molecules are combined together, they tend to form stable structures, and they are usually used to modify the physicochemical properties of one molecule. Of course, there are other ways to modify these properties, such as forming like salts by pairing one molecule with a counter ion, or to pair one molecule with water or any other solvent to form hydrates or solvates. But in this work, we just were focused only in co-crystals. So two different combinations of two different molecules to modify physicochemical properties. So when these two molecules pair together, they form crystal structures, and it's of large interest how we can be able to predict how these two different molecules can be combined. So currently there exist several theories about how co-crystallization can happen. So starting from molecular complementarity, Fabien's method, where it was found by looking at molecular descriptors that if two molecules have similar size and polarity, then they tend to form a stable co-crystal structure. There are also some other theories about the hydrogen bond hierarchy known as ether rules, where the good donor and acceptors tend to form more stable co-crystals. On the other hand, there are methods including the molecular electrostatic potential surfaces, where by the difference of the energies of the single molecules and the combination of the molecules, we can have an estimation about the relative stability of the co-crystal without the need of knowing anything about the crystal structure. There is another theory as well about counting the energetic stability of the crystal structures. So looking on two different crystal structures of single molecules and the crystal structure of the co-crystal, and by calculating this energy difference, we can tell if that the co-crystallization is usually the most energetically stable way. So, of course, there is a lot of work around co-crystals, and they're quite important basically in two different areas. So they can be very important as pharmaceuticals, because they can modify the physicochemical properties of the active pharmaceutical ingredient, like in paracetamol, and then form some, but without changing the drug properties itself. So for instance, paracetamol, the pure paracetamol cannot be easily tableted, but when it's paired with theophylline, then stable and better tablets can be formed. Moreover, In the area of organic materials, co-crystallization is an important way to modify the electronic properties of one molecule. So usually in this category, we have the charge transfer complexes where we need a good donor molecule with low homo energy, such that the electrons can easily jump to the good electron acceptor with low LUMO orbital and get the electrons and to enable this conduction in the co-crystal. So in our work, we first started by gathering all the co-crystals in the CSD and observing the trends across it. So here we can see the map of the whole co-crystals that exist in the chemical structure database, and they are color-coded based on the type of interactions that connects the two different molecules. So we can see that the largest area is dominated by hydrogen bonding. The most of the co-crystals are because of this hydrogen bonding between the two different conformers. We have also calculated the homo-LUMO gap between the pairs across the map. And so we can see that the homo-LUMO gap in the region of the weak interactions, which is basically the area of pi-pi combinations, is lower in comparison to the other type of co-crystals. So this work performed together with Daniel, who is giving the talk after me. And there is, by clicking to any of the dots on the map, it gives a direct link to the CSD, and we can see the information about the crystal structure of each co-crystal. So looking now not only the crystal, but on the single molecules that form these co-crystals, we split them as coformer 1 and coformer 2. So usually the coformer 1 is the molecule that has the largest molecular weight, and coformer 2, the one with the lowest molecular weight. And we wanted to see what is the safe distribution of the co-crystal components. So by creating the PMI plots showing on the corners the most linear, the most circular, and the most spherical molecules, we can see that usually the APIs or the coformer 1 tends to cover a larger area of the space, whereas the pairing molecules tend to be either mostly linear or circular. So to move on, we want to find the problem that we have to solve. So the thing is that given two different molecules, we want to be able to get a ranking. So to get a score for each pair, such that the combinations that have the highest score are more likely to form a co-crystal, whereas those that have a lower score are less likely to form a co-crystal. And with that way, we can avoid experimenting on co-crystals that are not likely to exist. So the issues we have here is that the molecular pairs should be ordered invariant. So independent of the order we give the molecules to a model, then they should get the same, exactly the same score. And also another problem, the major issue in general in material science, is that we didn't have any negative data to train a machine learning model, because usually in the databases, we only have information about which crystals exist. And we don't know which pairs of molecules cannot form a co-crystal because there is no crystal structure for them. So this problem has been tackled for many other groups. So they have done lots of amazing work about how we can predict co-crystallization. The most of them are basically trying to train some binary classifiers, which means that knowing which pairs form co-crystals and which pairs does not, so the positives and the negatives, they're trying to find the best line to separate these two classes and then train a model on them and then be able to rank any new given pair. So instead of that, we wanted to entirely drop out the negatives because they were unreliable and we don't have much information about them. And we tried to use a method called one-class classification, or else anomaly detection, which is basically focused only on one class of materials. So we are trying to find where the density of this data is, and then to see if we are able to add any new pair in this region. So the first case study was the pi co-crystals, and it can all be summarized in this closed loop. So we started from database analysis. We tried to get all the known molecular pairs on the CSD, and then we also tried to design a second data set about several unknown but possible molecular pairs from Zinc-15 database, which can be synthesized in the lab. So we used the one-class classifiers by trying to define the area in which the most of known molecular pairs can exist, and then to map any of the unknown molecular pairs in between this region. So after testing several machine learning algorithms and had a ranking for some good pi molecular pairs, we wanted further to optimize the suggestions and then select some cheap and available molecules, and then also to optimize our selection further by selecting molecules that have high score and similarity to TCNQ, which is a molecule very well known for electronic applications in co-crystals. So after that, experimental work performed in a group, we were able to make 2 new co-crystals. So again, the workflow, how we created the 2 databases can be described here. So starting from 8 polyromatic hydrocarbons, we created the 2 data sets, the one from the CSD with 1,700 combinations, and then one with 21,000 possible molecular combinations. We described them as 2 vectors with molecular descriptors that we got from Dragon software. And then we were able to make the 2 datasets, the labeled and the unlabeled. So this work drove to the synthesis of these 2 new forms. And by looking at the density of states of these 2 and measuring the band gap, we found out that the band gap of the second co-crystal was quite low and was in the region of semiconductors. And that was a proof that co-crystallization modified the electronic band of a single molecule, which was the first conformal that was pyrene. So moving forwards now, so this was like a case study that we were doing for the first 2 years. And now we want to scale this up and then trying to build a predictive model that can cover a bigger class of co-crystals, so independent of the interactions between the 2 molecules. So to do that, we followed the approach described in this plot. So first of all, we extracted all the co-crystals deposited in CSD, independent of the type of bonding that connects the 2 molecules together. Of course, we have only positive labels because all of them are known structures. After that, we tried to find different ways of how to represent the molecules. So we tried some fixed representations or some learned representations, which I'll explain later what exactly the difference is. So after that, we built a model that we used the same model as one-class classifier we used for the pi co-crystals case study, but we adjusted it such that to add some more hyperparameters, and then to have as a training task how to reduce the reconstruction error of our architecture, which was an autoencoder. At the same time, we were trying to gather some external co-crystal screening data from literature for which we had a knowledge about the labels. So several experimental groups have tried to perform in-silico co-crystal screening in the lab. And so they report the outcomes. So if a molecular pair gave a new co-crystal, then it is labeled as 1. And if a molecular pair cannot give a new crystal, it was labeled as 0. So using this external validation dataset, we were able to validate our trained models and see how well they perform on data they have not seen before, which have 2 classes. So the first part regarding the data extraction, we used the CSV and the Python API with some constraints such that the structures should be only organic, not polymeric. They should have 3D coordinates. We also dropped out the duplicates that crystals that have exactly the same unit molecules. We also tried to include different stoichiometries, but the structure should have exactly two different molecules. And then neither of the molecules should be a solvent, so we excluded all the pairings with solvents. So from this search, we get around 7,400 molecular pairs, which are known to form co-crystals. After having our data set, we want to see what's the best way to represent our data. So of course, there are several ways to represent a molecule, and we picked the two most distinctive ones. So is the molecular properties that has been extensively used. Either we can represent this as a fingerprint, like a bit string with zeros or ones, depending on the functional groups each molecule has. We also tried to use some learned molecular fingerprints, which is basically can be summarized in this graph. So these models are pre-trained in a very large corpus of molecules by masking some of the nodes. So if we see the molecule as a graph and then masking some of the atoms, let's say some oxygens, some nitrogens, so they're masked randomly, and then the model is trying to find what is the atom here that is missing, that is masked. So these pre-trained models can be later used to get a fingerprint about any given molecule. And they have quite better knowledge about what a molecule is because they have been pre-trained in large databases above 1 million molecules. So after selecting the 4 different techniques of represent a molecule, we tried to design our model architecture. So the architecture is basically based on a set transformer, which is a model, an architecture created from Lee et al. And it is based on a permutation invariant function, which means that dependent on the way we give the molecules on the input, the output is not changing. So we can imagine this as an autoencoder that by giving the two molecules as two combined vectors, we try to encode them in a latent dimension, which is smaller in length, and then we try again to decode them again. Our aim is to minimize the reconstruction loss. So how better we can reconstruct the two molecular pairs that are given as an input to the encoder. The hyperparameters that we were trying to adjust was the learning rate, the batch size, the number of epochs, the weight decay, and the dropout, which were like the parameters of the network that we were trying to change them such that the reconstruction loss of the model can be minimized. And to do that, we used library cont1b, weights and biases, and enables for hyperparameter screening quite efficiently. Further on, we wanted to add an uncertainty component to the model. So not only to have one score for each molecular pair, but we want also to know how sure is the model that this is the correct score or how unsure. Because that might be important, especially for experimental planning, because either we want to select a molecular pair that we are very sure it's going to form a co-crystal and has a high score, or we might want to explore more and so select a molecular pair that has a really low score but a very high uncertainty of that's a negative. So I was looking for several ways how we can incorporate uncertainty estimation in a neural network. And there are several ways. So either we are basically focusing on measuring the feature space distances or the distances of the latent space, or we train ensemble models. So we train 10 different models and then we take the average of the predictions. Or we use Monte Carlo dropout, which is what is used in this work. So how this technique can be summarized here is we are hiding some nodes of the network randomly, and then it's the output is actually like having 10 different models, but we don't, but in one. So it's an average of the predictions of the hidden nodes. So further on, we wanted to gather some available data sets because the issue with the co-crystal design is that there are no reported negatives. So there is not a database reporting negative molecular pairs. So we tried to do that together with Ioanna Sovago. So we were searching all the publicly available data sets that exist in literature. We gathered manually all of them and represented them in the form of correct CCDC smiles. We labeled them with 1 if they were reporting successful and 0 if they were reporting unsuccessful experiments. So it should be noted that not all of these cases were reported in the CSD with the crystal structures, because in some cases molecular pair was reported as positive just for some IR or PXRD observations, and not by solving the final crystal structure. Also, some other observations were that some molecular pairs have been reported as negatives in one paper, and then after 4 years, this pair happened to be positive because someone tried to make the co-crystal. So yeah, even if gathering the data from literature, sometimes the negative data cannot be extremely reliable because someone at another point might be able to make the structures. And so having now collected all the data, having built our model, we have everything set, and we are trying to train our model based only on the known co-crystals extracting from the CCDC. So these are the output of the won't-be library that were used, and showing how the hyperparameters are tuned. And on this panel, we can see how the validation accuracy is changing by modifying our hyperparameters and by decreasing our reconstruction loss. So the important thing to observe here is that when the reconstruction loss was minimized, then at the same time the validation accuracy was maximized on data that the model has not been trained on. So there is a quite nice trend between validation accuracy and the reconstruction loss, meaning that by training the neural network, just aiming to decrease reconstruction loss of its training data, we can achieve very good accuracy in external data. And that showcases that we don't really need any negative examples to train a model that has decent accuracy. So here we can see the performance of the models in the external validation sets. So by using our 4 different representations, so the molecular descriptors, the Morgan fingerprint, the DNA fingerprint, and the Kembertner fingerprint, which refers to a pre-trained NLP model, we can see that the actual positives tend to get high scores and ranked high in all the models, but the DNA fingerprint and the Morgan fingerprint tend to have better discrimination between the real positives and the real negatives. So the real positives tend to get higher scores than those that were negatives, giving an accuracy above 75%. Later on, we want to see what's the uncertainty calibration tell us. So what kind of information we can get. So here we plotted the uncertainties based on the predicted and true label. So we can see that the uncertainty on the true positive and false positive, so the cases that the model regards as positive, is quite low, whereas the cases that the model regards as negatives, it has higher uncertainty because it's in one classifier. And it's interesting to see that, especially in the false negatives, so the model predicted it as negative, but it was at the end it was positive, tend to have very high uncertainty, which means that by selecting a point that has really high uncertainty might lead to a new co-crystal, which is quite different from the co-crystals the model has been trained on. Further on, we wanted also to see if our predictions make any sense, like physically. So And to do that, I used supply values. So it's a library to be able to find where, in which parts of the input your model pays more attention or has the higher weights. So for some test cases, so I took some positive examples with diclofenac, and then I was trying to look in which part of the two molecules the model had the highest weight to give a high score of them. And actually, it made quite a lot of sense that it was looking at the OH group in one molecule and then the nitrogen group on the second molecule, so for forming the hydrogen bonds. And of course, because it was trained in lots of pairs with hydrogen bonding, it was able to the predictions to extract this trend as well. Then we wanted to compare our models with some other methods. So we selected two physical models, which is the MEPS, which is electrostatic potential, and the COSMO-RS, which is basically a model about the difference of enthalpies. And then two machine learning models, which are binary classifiers, and they provide their code online, so we can test on some well-known APIs. So we can see that in most of the cases, our model, which was trained only on positive data and in an unsupervised way, had similar or even better accuracy with the other physical or ML models. So our models is the Morgan fingerprint and the CNN model. What we really went bad was in itraconazole, which is a very large molecule, but with also a very unique groups with these nitrogen groups, aromatic rings, which is not a grouping that can be observed in the CCDC quite often. And so at the end, after we tried to incorporate these models to an online graphical user interface, whereas by giving the molecular pairs we are interested in, so the molecule 1, the API, or the molecule 2, we can select which of the pre-trained model we want to use, and then we can get a ranking and also an uncertainty. So where we can select some points with really high score to be synthesized. So yeah, so to summarize, we saw that there is applicability of one class unsupervised approach to the whole range of CCDC, and not only in the limited case we started with. Of course, there are several machine learning models that do a great job in co-crystal screening, but our case is that we don't need any negative data to train on, and we can train our model just by aiming to decrease the reconstruction error and then be able to rank any given molecular pair. And also the online GUI is available for quick accessibility, and everybody can just use it and test it. So yeah, to close my talks, I would like to thank my supervisors, both from the Liverpool and CCDC, and yeah, I'm happy to take any questions.
So are there any? No, I think first a round of applause. Well done. That was an excellent talk, Katerina. So now I'm going to challenge you all now. We've got a little bit of time. We've got 3 minutes. So are there any questions out there? Put your hands up or unmute your mic if you want to. Oh, yeah, Isaac's got one. Unmute your mic, Isaac, and ask away.
Hi, can you hear me, Katerina?
Hi.
Hi. You may have already mentioned it, but does your model allow for mixed stoichiometries? The images suggest one-to-one, but obviously you're looking at quite a lot of different systems.
I mean, here we can only, it is only trained on 2 different combinations, but it's because if we have like co-crystals with 3 different molecules, then it sure can be readjusted to include different types of different molecules. So otherwise, only the stoichiometry. So we have 2 molecules, and which is the stoichiometry. So it can be able to predict if it's going to be 1-to-1 or higher than 1-to-1, but not. It cannot directly tell you, oh, you have like 2 molecules of this API versus 1 of the second. So it cannot be that accurate on that.
Okay, it sounds very powerful, very interesting. If I could have a second question,
Yes, of
you
course.
say co-crystals throughout. I take it you're putting organic salts in as well, right? The distinction between co-crystal and salt is, a little bit vague.
We didn't include like any salts or any solvents, so we just took the combinations of two pure molecules. If you have a data set with including both salts or including both pairs of one molecule and one solvent, then as long as the model is trained with all this data, then it will be able to give predictions for this data as well. But in this case, we just only looked at the two different molecular pairs.
Yeah,
Not
excellent.
including
Thank you.
salts or
Or solvents. Yeah, cool.
Okay,
Thank
excellent.
you. That was very interesting.
Okay, well,